Hello, my name is Russell for nandland.com, and in this video I'm going to talk about how Boolean algebra works inside of your FPGA. I'm going to talk about some complicated Boolean algebra equations, show how gates inside of an FPGA can be used to write those complicated Boolean algebra equations. So in the previous video I introduced the concept of gates. I introduced AND gates, OR gates, NAND, XOR, and NOT. And in this video, I'm going to show how those gates can be used to be joined together to create some complicated equations. So first of all, why is this important to FPGA designers? It's a perfectly legitimate question. The reason is that when you're writing code, when you're writing your VHDL and your Verilog code, you're going to be writing code that requires, at a fundamental level, these gates to be used to solve your equations. And I don't necessarily mean mathematical equations, I mean logical equations. So you might have maybe you have some switch outside your FPGA that looks, a couple switches like this, and you want to know, if either of these two switches are high, set to 1, then I want to light up some light bulb out here. That might be something you might want to do with an FPGA. It's a very simple thing you might want to do, but it might be something legitimate. So how would you do that? You have to use VHDL and Verilog to write that says if input 1 or input 2 is equal to a 1, then light up the light bulb. If you haven't figured out, that's done with an OR gate. So you might have an FPGA that looks like this. Here's your FPGA right here. And that's what your FPGA does. If either of these two inputs are a 1, then your output is going to be a 1. Now there's more complicated things than just an OR gate. You might have gates cascaded together. So that's what this video is going to get into, is how those equations work and how your gates can be used to use those equations. So let's say I have some equation like this. A and B or C. I drew here a dot and I drew here a plus sign. In Boolean algebra equations, the dot means an AND. The plus sign is OR. And a line over the top is NOT. So with that, we can start to get a feel for what this equation represents. So your output is equal to A and B or C. A, B, and C are your inputs, out is your output. So if we were to draw this out, here's how I would recommend doing it. You have on the left here A, B, and C. And so what does your middle area here look like? This might be your FPGA. What would your FPGA look like if you wanted to draw that mathematical equation out? Well, you know that A and B need to be joined together. So there you go. That's an AND gate. Or C. So the output of this can go into an OR gate here. And that's your output here. And then we need to connect C to the other input. So there you have it. This is your FPGA if you were to write that code in VHDL or in Verilog. Now this isn't exact VHDL and Verilog syntax, but this is pretty much what your FPGA would end up doing. It would be putting down these gates, and if you have these inputs, that output, this is what the inside would look like. Let's do another example. let's make up something here. We'll do not A or not B or not C. So we have A, B, and C as our inputs here. Our FPGA, our black box, goes here, and we have one output. So what would this look like on the inside? Well, we know, first of all, that we need to invert all three of our input signals, which can be done with the not, like this. And then the interesting thing about OR gates is that it doesn't matter if you were to take these two and then OR that with C, it wouldn't make any difference. If you took B and C and ORed it with A, you'd get the same result on the end, on your truth table result. So let's draw this. An OR gate here and an OR gate here. These get wired to this input, this get wires here. Take that like that, and there you have it. So not A, not B, not C go into this OR gate. The output of that OR gate feeds this OR gate. The output of that OR gate feeds your output. So this could be a very viable, perfectly viable FPGA. It's a simple one, but this could be what's inside of your circuits. Now, when you're writing your VHDL and your Verilog code, you're actually putting down these gates, and you're actually creating these wires. These are wires. Where I'm drawing here are actually physically wires inside of your FPGA. So that's kind of a neat thing to think about. I want to talk about what the truth table for this particular circuit would look like. So basically what I'm saying is when is the output equal to a 1 and when is the output equal to a 0? We can actually derive that with truth tables. In the previous video, I showed you what truth tables looked like for all your different gates. And now I want to say, so what does the truth table look like if you have a more complicated thing than just one gate? What is the truth table for the entire circuit or the entire Boolean equation look like? We can do that too. So your inputs to your truth table now are A, B, C, instead of I1, I2, I3. ABC, and you have one output called out. So first of all, on your inputs, we can fill in all the different combinations of what your inputs can be, and it's just all the different bit zeros and ones, and usually you count in binary for truth tables. So counting in binary would be 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and the very last one is 1, 1, 1. You now have 8 possible input combinations because you have 3 inputs. So mathematically that can be represented as 2 raised to the number of inputs is the number of combinations possible for any particular truth table. So if you have 4 inputs, 2 to the 4th is 16. 16 possible combinations. 5, 2 to the 5th is 32, etc. So for the previous cases we had 2 inputs, 2 to the 2 is 4. Here we have 8. So let's draw this truth table out. And we have to just do this. This is a manual exercise thinking about what this equation really represents, and we'll be able to draw the truth table for this Boolean algebra equation. We already drew the circuit, now let's figure out what the circuit is actually going to do. So not A, or not B, or not C will give us an output of 1. So not A, or not B, or not C. This is going to be an equation where most of the time the output is actually going to be a 1. The only time where it's not a 1 is when this is not true. So when either A or B or C has a 0, the output will be a 1. Not A or not B or not C. Basically, this is saying, are any of your inputs equal to 0? If so, your output is going to be a 1. So not A. Where does not A occur? Let's do that one. Oh, here's not A right here. Here's not A. Here's not A. Did I miss one? I did. 0, 0, 0. That's a possible input combination as well. So not A. This is a possibility for not A. This is not A. This is not A. This is not A. Where does not B occur? Not B occurs here. Not B occurs here, here, and here. Where does not C occur? Not C occurs here, 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 and here. Now, these are all ORed together. So if you see any check marks here, that means that this particular line is going to produce a 1. So 1, 1, 1, 1, 1, 1, 1. Here, the very last combination is the only spot where the output is equal to a 0. Every other time, these input combinations are going to be setting the output to a 1. Now, there are always other ways to do Boolean algebra. There's always other ways to describe the same circuit. So, for example, this is kind of a complicated equation to think about mentally, but really what we're trying to do is figure out when are A and B and C all set to 1, and then invert that. So, if you wanted to, you could do something even simpler. You might want to do an AND gate, and an AND gate, and then an inverter. So this could be A, this could be B, this could be C, A and B and C. If you were to just draw this circuit without the inverter, then it would be, you'd get as an output 0, 0, 0, 0, 0, 0, 0, 1. But the inverter inverts all of your outputs, so now we actually get what we started with for this equation here. So just wanted to show that there's always other ways to do your Boolean algebra, but you don't generally need to worry about the simplest way to do it. As long as you get the right answer, then you're fine. We'll do one more example. And we'll draw the truth table for it. So we'll do not A and B or C. So quickly I'll just draw the circuit here. First A, B, C, B or C. Let's see. Here's B or C. Actually, so one thing I should point out here is that the AND is going to have precedence in this particular circuit, the way I wrote this here. So if I were to draw the B and the C first, that would actually be incorrect. What really happens first is not A gets inverted, and then A and B together go into an AND gate, and then the output of that gets ORed in an OR gate with C. So there you go. That's the correct schematic for that particular Boolean algebra equation. If I had done it the other way, where B and C had been ORed first, that would have produced a different truth table. So there you go. That's the circuit. And now I'm going to draw the truth table for that Boolean algebra equation. So we have as our inputs A, B, C. and all possible combinations. There's 8 of them. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. There you have it. Those are your combinations. Here's your output. So not A and B or C. We could start with the or C pretty easily and knock those out. So where is C equal to a 1? In those situations where C is equal to a 1, your output will guarantee to be equal to a 1. So we can check those off. Here's 1, here's 1, here's 1, here's 1. Okay? So we know already that the output is going to be a 1 here. We can actually fill that in if we want. 1, 1, 1, 1. Doesn't matter what A and B happen to be. It's going through an OR gate with C. So we know for a fact that the output is going to be a 1 for those input combinations. So now we need to figure out if there's any other combinations where the output will be a 1. And the only other combination where that can be is when A is equal to a 0, not A is true, and B is equal to a 1. So that happens when A is a 0 and when B is a 1. So when these two things are true, the output will be a 1. And we can look down just A and B and figure out when that happens. This is not A, but B is equal to a 0. This is not A, B is equal to a 0. Here we go. This is not A, B is equal to a 1. So not A and B happens right here, and it happens again right here. So we've taken care of this one already with the OR gate, but this one we have not taken care of. So we know that this one becomes a 1. So there you go. Any place where I have a check mark or a circle, those are the situations where the output is going to be equal to 1. And the other times, here, here, and here, the output is equal to a 0. So there you have it. This is the truth table for that particular circuit. Now, one thing I want to make clear is that FPGAs, up until this point I've kind of led you to believe that FPGAs actually have little AND gates and OR gates inside of them. That's not actually true. I said that because it was easy. I'm sorry, I lied to you. But really what they have is a lookup table. What is a lookup table? Lookup tables are fascinating pieces of circuitry. Look up table, or LUT. When you hear people talk about LUTs, they're talking about lookup tables. Lookup tables you can think of as a box. The simplest FPGAs that came out in the mid-80s had 3 input LUTs. 3 input lookup tables. So there were 3 inputs and 1 output. So those circuits that I was just drawing with 3 inputs, A, B, and C, can all be represented inside this LUT, this 3 input lookup table. So think about that for a second. Any possible combination of circuits that you can think of with 3 inputs and 1 output, doesn't matter what that output is, if it's the one I just drew here, the one I drew previously, anyone that I haven't drawn up here that you can think of, this single 3 input LUT can implement that Boolean algebra equation. Pretty neat. So these are very flexible pieces of circuitry. They are one of the 2 fundamental components inside of an FPGA. So very important to understand what is a lookup table. What is a LUT? I'm going to say it again. A lookup table can implement any Boolean algebra equation with 3 inputs, a 3 input LUT. There can be a 4 input LUT and sometimes even a 5 input LUT. So a difference between a 3 input LUT and a 4 input LUT is that a 4 input LUT can take 4 inputs and produce any Boolean algebra output given 4 inputs. So any truth table you can draw with 4 inputs, the 4-input LUT can do inside of an FPGA. Very important piece to understand here. The tools, the FPGA tools that you are using, that you're going to be using, are able to program these LUTs given your Boolean algebra equation. So when you turn on your FPGA, these LUTs get programmed to all the individual Boolean algebra equations that are needed inside of your FPGA. Pretty fascinating pieces of circuitry. Again, I said that LUTs were one of the 2 most important pieces of circuitry inside of an FPGA. The second most important part of an FPGA is a register or a flip-flop. And that is going to be saved for a future video because it is a complicated topic and it's going to take some time to explain. So definitely subscribe and stay tuned to hear more about how FPGAs work and what is a flip-flop. Thanks.